Well, first of all, thank you for the invitation to this summer school. So my name is Freek Stulp, as you can see, and I am head of Department of Cognitive Robotics at the the Institute of Robotics and Mechatronics. And we are part of the German Aerospace Center. Think of it like the NASA of Germany. And I'm going to speak about robotic reinforcement learning today, but also some other things. And I will... And I will jump right into the beginning of the talk. So I was looking at the agenda for today, and I saw I'm in the assistive robotics part, and that's fine because we also do assistive robotics. It's also a summer school about AI, so I wanted to mix in some AI also. So I'm going to have two main parts of the presentation today. One is more application-driven, and that's about assistive robots. And the other one is more research-driven. It's about AI and more specifically reinforcement learning directly on real robots. And as you see up here, maybe something about the Institute of Robotic and Mechatronics. We are a institute, about 200 researchers, employees, working on the full stack of robotics. So we do mechatronics, we build our own robots, we control them with our control algorithms, we do teleoperation, perception, the AI. So I'm the responsible in the cognitive robotics department for this last part on artificial intelligence. And today I'm going to speak a lot about assistive robots on Earth, because our institute does a lot of space research and space missions. Here you see an example where Alexander Gerst, a German astronaut, controlled one of the robots in our labs. So if you're wondering why is a person from German Aerospace Center talking so much about robots on Earth, that's because that's the focus for today. We have a lot of projects related to space, and if you're interested, go to our website. So the outline, the first part of this talk will be very strongly about assistive robotics. For the session, I think that would be appropriate, and in particular on a technology we developed called shared control templates. Oops, wrong way. The third part will be about robotic reinforcement learning and how we can make this more efficient and more safe with these shared control templates. And in the middle, so that you understand the relation between the two, we're going to play a little game. It's called Hunting the Thimble. If you don't know what that is, that's fine. I'll explain later. So the first part on assistive robotics, we have developed the EMG Control Daily Assistant, or also called Eden. Oh, sorry, that's my cat wanting to play. And this is a wheelchair essentially with an arm attached. And from the body of the person in the chair, we have EMG sensors, so they measure signals that are sent to the muscles, and these signals are then converted into movements of the robot. So in the top row, you see Annette. She's doing a PhD in my department, and one of the researchers working on this system. And at the bottom, you see examples of experiments or tests, that we have done with participants with severe motor disabilities and who use this system to actually perform tasks of daily living. And I'll speak more about that later. So that's Eden, the system, a robot with an arm and a hand. And one challenge with this system, or overall in assistive robotics, is that you often have very low-dimensional, noisy commands. So EMG, we have 3 sensors. It gives you a 3D signal. It's very noisy. How do you convert that into signals for the robot so that it moves in a task-relevant way? That's the second point. How can you provide support that is relevant for the task at hand? Right, that's an important question. And finally, how do you ensure that the user always remains in control? We don't want to develop a system where you press a button and it says, make coffee or pour water, and the robot does it all. The wheelchair does it all autonomously. No, we want the user to remain in control, to be the locus of control. So these are our aims with this system, and what is challenging, let's say, with the standard approach to this is that your user inputs with something called translational control. For instance, you have a three-dimensional input, will map to just X, Y, or X, Y, Z, right? As we see here in this example. That is a very limited range of motion, which, with which you can do not many tasks in everyday life. Consider, for instance, pouring. If you can only move in this direction, you will not be able to tilt the end effector. Wait, I brought a bottle for this. And that means you would not be able to pour water, right? So how do we deal with that? Well, we have these shared control templates. And what they do is that they change the motion, they have input mappings that determine how the robot moves depending on the inputs. So if you're pouring later on, two of the inputs from the human, the motor commands, they will determine the orientation, and one will determine the z-axis, right? So in the beginning, you're moving like this, and if you go closer to the cup, then it will start tilting. And then furthermore, we have active constraints that limit the range of motion. So you're not allowed to pour like all of a sudden like this and everything will spill out. So there are these constraints which further support the human in completing the task successfully. And then we have a finite state machine, which basically takes you through the different phases of the action. So in the beginning, if you're far away from the cup, you can move in translational control and the bottle doesn't tip. If you come closer, the bottle starts tilting. And in the end, you pour like this. And this depends on the distance to your target object. And I have a video for that, which should, yeah, it seems to be working. So here we see the wheelchair. You can see the person sitting in it just there. And currently it's already in a state where the bottle is tilting towards the target cup. So it's important that the robot knows where the cup is. We have perception for that. And now it's in a state where it's starting to pour the liquid. So the human is actually giving the commands for the robot to move, but the robot moves in a way that is relevant to the current task. Okay. So now basically the pouring is done. The human gives the commands to go back again, and it will switch to a state where it's now tilting away from the target. And when you're far away, it switches to translational control. And then again, you can put the object down and you've achieved the task. Here's another example. So again, this is a control with a 3D joystick, not EMG, but the user is providing only three-dimensional input signals for the robot, but the robot knows about the door, it knows about how to move to open the door, and it's controlling all of its degrees of freedom at the same time in order to achieve this task. And this is, let's say, very difficult to do if you do not have this kind of support. This will take hours, maybe even days, to move the end effector exactly in a way that you open the door without bumping into anything or causing a mess. So that's the shared control template approach and why we've done it and some examples. Now, a brief summary of results. Of course, we have more in the papers, but our aim here is that people are not frustrated doing these tasks by having to switch all the time manually or with other signals between different modes of operation. And we can see here that with shared control, when you perform these tasks, it's much, much, much faster than if you do what is called in this field manual control, which is still obviously controlling the robot with these signals, but that's the name that they give. I'll skip the whole body motion controller right now, but this is essentially coupling all the degrees of freedom of the robotic system to together achieve this task, right? So you're moving only at the end effector, and the entire robot wheelchair will actually move along with the end effector, and that's what enables us, for instance, to go through the door. I think the most impressive example is of how this all comes together, the whole body control, the shared control templates, was a few weeks ago when Matthias, our pilot, as they are called, in the Eden system, which you see here, won the Cybathlon challenge. So the Cybathlon is a 2-yearly event where basically it's a competition for assistive technology. And we entered this year, And we won, let's say, the preliminary phase, the challenges, the Cyberthon challenges. And with our system, we performed many tasks in 5 minutes. And yeah, we won this competition, so we're very proud of that. And next year, this were the preliminary challenges. Next year, the actual competition will be in Zurich, and we will go there with our system and Matthias, and hopefully win there also. Yeah, if you want to see this video, it's a bit longer. Here's the YouTube link. I can post it later in the chat. If you want to read more about this, this is Gabriel Carré. He's a PhD student in my department, and he is sort of the main developer of the shared control framework. Okay, so I'll come to part 2. I forgot to say this in the beginning. If you have questions, these parts are quite different. If you have but nevertheless, I'd like to sort of tell the entire story and have the questions in the end. So I now come to the second part, hunting the thimble, which essentially leads up to the final part about robotic reinforcement learning. So some of you may have already wondered or Googled what is a thimble. So a thimble is a small metal or plastic cap with a closed end, and you basically put it on your finger when you're sewing, so that you compress needles through cloth and also protect yourself from not getting the needle inside your finger. And actually, this is completely irrelevant for the game or this talk, but that's where the expression comes from. What is important about the thimble is that it's small, right? So it's easy to hide in a room, and that is the game that you essentially play. So the game is like this. I think everyone knows it, but maybe not under this name. Let's say Alice and Bob are playing this game, and Alice leaves the room. Yeah? Then Bob hides a small object, the thimble, a USB stick, a key, whatever. And then Alice comes back, and she has to find the thimble. And you know, a thimble is a small thing, so if you hide it in a room, it's very difficult to find. So Bob helps Alice by saying, "Oh, you're cold, cold, colder, warmer, warmer, hot, hot." Okay. Probably everyone has played this game as a child with their parents. And then this essentially temperature gradient allows Alice then to home in to the thimble and then hopefully find it. And then everyone is very happy, and the game is fantastic. So it may seem like a bit of a boring game, but children absolutely love this. Highly recommended. Hours, you can do it for hours. There's a variation. So yeah, this is an illustration of that. It's a temperature gradient that Bob creates for Alice to more easily find the thimble, because otherwise she would just have to exhaustively search the room, which is, you know, boring, and also kids don't like doing that. Coming to the next slide. Now, I have a variation of this game, which is important for this talk. It's the fast version. So in this version, Alice leaves the room, okay, and then Bob hides a small object, as before, and then Alice comes back, and then Bob just says, "Yes, the thimble is in the cup in the drawer," yeah? And then Alice finds the thimble. Now, this is a very boring game. I don't recommend playing it like that with your children if you have them, because they will be angry that you gave the spoiler alert and told them where the thimble is. But I think you'll agree with me that if you want to do the game quickly, this is certainly the faster variant of the game. It will become clear why I'm telling you this later. Now there's an even faster version, which I call passing the thimble. Okay, so Alice leaves the room, Alice comes back, and Bob just gives the thimble to Alice in her hands. Yeah? So this is what I call passing the thimble. And this is like a super efficient version of hunting the thimble, the game. Okay, so I think this is very related to reinforcement learning. Yeah? It's about sparse rewards, it's about dense rewards, and these are, let's say, technical terms. And I wasn't sure about the audience and your background. I've tried to make the presentation in a way that you don't require much knowledge about reinforcement learning, so no technical background in reinforcement learning. My expectation was that everyone knows essentially what reinforcement learning is, maybe from courses, maybe from reading about it in newspapers or online, and that you basically understand that reinforcement learning is an approach where you give rewards or penalties to an agent, and what the agent has to do is find out the actions that optimize getting these rewards. Right? For instance, this is what you do when you train dogs. Yeah? So you give them rewards, or you penalize them if they do something bad, and then dogs learn how to do the right thing. That is like very entry-level reinforcement learning, and I really assume that everyone knows this, but I thought I'd lay the foundation to ensure that it's really the case. So this hunting the thimble, I think, is related to reinforcement learning in the following way. When you do reinforcement learning, usually there's some task that you want the robot to solve, right? I'm thinking mainly about robot reinforcement learning today. And solving the task is basically like, okay, is the door open? Did you successfully open the door? Is there a peg that you placed in the hole? Is there a cup that is now successfully in my gripper or some other object? Is the solar panel clean? That's something which is important in space robotics. And this is what I would call the task, right? This is what you want the robot to achieve. And this is usually expressed in what I call the primary cost. So that means the robot gets like 1,000 points if it completes the task and 0 if it doesn't. Right? It's like the big bonus, and that's why the robot is learning to solve this task. This primary cost is usually qualitative. It's like, did you solve the task or not? Yeah? It's usually sparse. In many tasks, you say, yes, you have now the cup in your gripper, or no, it's on the floor and you failed. So it's usually a sparse reward. It's usually a terminal cost, and that means that it's or reward. That means it's given at the end. Only at the end of an episode do you know if the robot achieved the task or not, and that's when the robot gets the reward for succeeding or the penalty for failing. And furthermore, obviously, this primary cost is very task specific, right? So you have to sort of, from the sensors or a human looking at the task, figure out did the robot achieve the task or not. And the primary cost, let's say per definition, is task specific. I'm clicking the wrong computer. So there's also usually in these cost functions what I call a secondary cost. And that is, did you do it well? Okay, so you solved the task, okay, but did you do it well? For instance, did you do it quickly? Did it take you 10 seconds or 2 hours, right? You solved the task, it just took a very long time. Did you do it energy efficiently? Also very relevant for robotics. Did you do it robustly? Did you do it smoothly? Did it look like very ugly in a robotic motion, or was it an elegant motion? All of these things are not essential for solving the task, but it's still things that we like robots to do. And that's why they are, let's say, always nice to have, as I say here. You would usually like your robot to do something quickly, elegantly, smoothly. And another aspect of these secondary costs is that they're usually quantitative. Okay, time, is a continuous variable. It can be 1 second, 2 seconds, etc. It's dense. So if you're measuring, for instance, jerk, okay, how jerky is the movement of your robot, you can measure that at each time instance. Right? And that's sort of the aspects of these secondary costs. Okay, then when the robot has done a task, you sum these costs up. You have only one cost for the robot. The robot is trying things, getting these rewards, this total cost, and then trying to optimize the cost with its actions. Yeah. Now, there's something going on in the background, and that's usually there's some developer, perhaps a PhD student, and they are thinking about explicit constraints and goals in their head when they're programming these cost functions. So, for instance, they may think like, oh, you should keep the cup upright, okay? The bottle upright, otherwise you're going to spill water. So then this person would then express this goal or this cost as a gradient. Yeah. So if you tilt, that's bad and you get a penalty. But if you keep it upright, that's good and you get a reward. Right. So we have this transition from having an explicit constraint in your mind to expressing it implicitly as a cost function and then giving this cost function to the robot to optimize. And my main statement in this talk is it's a much better idea that if you have an explicit representation of this constraint, to actually tell the robot about this constraint, right? And maybe now you see here the analogy to the thimble is that if you play hunt the thimble, if you create this gradient, that may be fun, but it's not going to be the most efficient way of doing it, right? But if you pass the thimble directly, if you tell the robot about the constraint, it knows about this constraint already, so it doesn't need to learn it anymore. And then you can focus on optimizing secondary costs instead. So to nail this story down about the thimble, hunting the thimble is, in robotic reinforcement learning terms, unnecessarily converting an explicit goal or constraint into an implicit cost function for your robot. Yeah. Now, unnecessarily is, of course, in the eyes of the beholder, right? This is not some formal proof. I'm being a bit polemic here, but this is what I call hunting the thimble. And passing the thimble is when you have this explicit goal or constraint and you make it to your available to your robot with some representation, for instance, through intuitive programming. This is passing the thimble. Okay, I hope that was clear. It's important for the rest of the story because now I get to the part about how this is relevant to robotic reinforcement learning. No, I explained that it's how do we implement this in robot reinforcement learning, and what role do the SCTs play there? So an insight that we had is that rather serendipitously, so we were developing these SCTs, we were working on reinforcement learning for robotics, and then we noticed that the features that support the user in Eden with the SCTs also provide support for reinforcement learning algorithms. And indeed, we found out that such let's say, support that we provide for the users, that similar concepts have been studied in reinforcement learning. So, for instance, freedom of movement is very important for humans, that they have a freedom to choose what they do, that they feel empowered. And in the shared control templates, that's what we want to achieve with this freedom of movement, that the user feels empowered. In reinforcement learning, you also need freedom of movement. Otherwise, you cannot explore you cannot try out things, right? In shared control templates, we have these active constraints. Remember, you don't want to pour too quickly, and this constrains the action space. That has also been studied in reinforcement learning, where it's called action masking. Reducing the action space, that's done in this SCTs with the input mapping. Remember, sometimes the human commands would lead to this kind of motions, and sometimes they would lead to this kind of motions. So you're changing the action space depending on where you are in the task. In reinforcement learning, that doesn't exist, but not that we found, but you can actually do that in a Markov decision process. And this was something we made up called transition space shaping. And furthermore, shared control templates have this distance function to determine how far are you from the object, and that determines the behavior of the shared control template. Basically, if you're tilting, or if you're pouring, or if you're moving in translational mode. That's also used in reinforcement learning a lot, these distance functions, and there it's called reward shape. So our idea was to use shared control templates in the context of reinforcement learning to provide support for the reinforcement learning algorithm so that it can learn better. First, an example task. This was done on the Sarah robot. It's a robot that we built at our institute. It's a collaborative robot. It works in industrial environments usually. But here we did a toy task where the robot is pouring. And actually the reason was we already had SCTs for pouring implemented on Eden, where actually users want to pour a drink. In industrial environments, that's not so relevant, but we took that task as a start. And looking at the time, I will now speak a bit more about the reward function design as we did before, and these primary and secondary costs. So the primary reward, remember, that's solving the task. Okay, so that's very task specific. And the secondary reward, that's basically do it fast, do it energy efficiently, don't bump into obstacles, etc. And those are the primary and secondary costs. In reinforcement learning, it's also important to distinguish between an immediate cost. I give it to you at each time step. You get a feedback after each action. Or terminal, you get feedback at the end of the episode when you've completed your task, or you think you have. And in reinforcement learning, for instance, a sparse reward function is a terminal reward or cost, which is given at the end. You solve the task, okay, you get 1,000 points. Did you collide? You get minus 1,000. Yeah? And that's given at the end of the task. So it's terminal because it's at the end, and it's primary because it's about achieving the task. And usually there's also some secondary costs, such as, one penalty for each time step. So this penalizes long movements. So the agent wants to become fast, and something like that is often given as an immediate reward. Now, these sparse reward functions, that's actually, let's say, the holy grail, or that's what you want from reinforcement learning. You just say 1,000 points, don't make it too long, and explore and do the rest, right? That's the promise of reinforcement learning. That's why it's cool. And the good thing about this is that these sparse reward functions, they're very easy to design. 1,000 points if you succeed, minus 1,000 if you collide. But they're not very informative. They don't contain a lot of information. It's the reinforcement learning algorithm's job to sort of extract the information out of that to determine the right actions. But it's very difficult to do so because there's hardly any gradient that the algorithm can follow. So you have very slow learning. So in the pouring task we saw before, after about 1,000 trials where the robot does this task, it hasn't succeeded. We used ping pong balls instead of water. The ping pong balls did not go in the target cup. It was just a mess. It wasn't learning anything, and it was colliding. It was spilling the ping pong balls all over the place. So very easy to design cost function, but slow learning because there's no gradient. Right? This is essentially not telling someone where the thimble is, and also not giving them hot, cold. You just have them look around, and they bump into stuff and can't find the thimble. So what you often see in reinforcement learning is that you design a reward function which is more informative. And this is called reward shaping. So what you try to do is that at each time step, you say, yes, it's going in the right direction. That's good. Or no, this is going in the wrong direction. Right? This is the hot, cold in the thimble experiment. And these reward functions are usually very tricky to design. So I show one here. I won't explain it. It basically says penalize the orientation, but not at the end, only in the beginning, because later on you need to change the orientation to pour the ping pong balls in the other cup. It's a big mess. But this is often what they look like. And if you go to the appendix of reinforcement learning papers, often you can find a cost function like this. And they are quite tricky to design. But the good thing is that they are much more informative, right? You're giving a gradient to finding the thimble. And this leads to much faster learning. So here you can see that in the learning curves, the blue curve is actually learning to do the task. So after about 700 rollouts, trials, it's already learned how to do that. And in the beginning, it was still colliding and it was spilling some of the ping pong balls, but also it learned to avoid that. And yeah, after about 1,000, it's really learned how to do the task without violating these secondary costs. However, yeah, this is the alarm bells that ring with me are that these cost functions are very tricky to design. If your task changes, you have to change them again. And it's sort of, for me, it ruins the nice story of reinforcement learning that you provide simple, sparse rewards and the algorithm will do the rest. So for me, this is the hunting the thimble alarm. So our idea, as I said before, is to pass the symbol. So we use these simple sparse reward functions, but we invest time in the time that you would invest in the reward design, you invest in the specification of the constraints that the robot has to fulfill. And on the one hand, that means providing an action space with SET. Okay, the actions that you do, how do they change the end effector movement, the end effector? And also enforcing these constraints, for instance, not allowing pouring like this, or for instance, if you're not close to the cup, the target cup, that you're not allowed to change the orientation. And we do that with the SETs. So how does that work? We have an action space. It's the 3D input. It's always 3D. And so before that was a user providing these commands. Now it's a reinforcement learning algorithm, as you can see here. So these actions are taken by the shared control template. It converts it with these input mappings and these active constraints into end effector motions, and this moves the robot, and the state is then given back to the reinforcement learning algorithm. And so the reinforcement learning algorithm it doesn't know that it's not interacting directly with the robot. It's not sending its actions directly to the robot. It's sending it to a shared control template, which then converts it into actions for the robot. But the reinforcement learning algorithm doesn't know about that at all. I'll skip over this very quickly. It was a simple policy, 2 hidden layers, not too many hidden neurons. We used different reinforcement learning algorithm implementations. And for the experiments, it's important that we had a variant where we have sparse reward functions, 1,000 or minus 1,000, and we had shaped reward functions, the tricky one that was very difficult to implement. And we either provided guidance with the SCTs or not. So either the algorithm was directly sending actions to the robot, or it was sending them to the SCT, which would then apply the constraints. And what does that look like? Actually, we had 2 algorithms. I'll just skip to the second one immediately. So if you have no gradient, there's no learning. And basically, you have these constraints violated at the beginning. And the robot essentially goes into some sort of depression where it's not doing anything anymore. It's like not telling someone where the thimble is. If you look for an hour, people say, okay, I give up. You're not giving them a gradient. I'm going home. Now, if you do a shaped reward function, so that's cold, colder, or warm, warmer, it will learn the task quite quickly, right? It means you have to implement this nasty function, this nasty cost function, but it works, right? And that's what is used a lot in reinforcement learning also. But we still see here with this orange curve, this represents the collision rate and the spill rate, that there actually are quite a few collisions with the environment. This is done in simulation, by the way. So the robot is simply bumping into the cup or into the table. So it's learning the task, but it's not doing so in a safe way. Now, if we pass the thimble, if we apply the SCT constraints during learning, I mean, first of all, it's obvious, and it should be, because that's why we were also doing this. Okay, I'll emphasize this again. So here, it's I see something in the chat. So let me explain this in terms of the thimble once more. Here in RL sparse, you're only providing at the end of an episode that you say, you solved the task, 1,000 points. Okay, that's like saying to someone, there's a thimble hidden in this room, and you're not giving them any further information. And the person has to look in the room, and when they find the thimble, you give them 1,000 euros. Yeah. And that means you will have it will take a long time. The thimble can be anywhere, you're not providing any information, and that's basically, doesn't work. In the shaped version, that means that you're providing a more informative reward. That means when Bob is saying, oh, you're colder, colder, okay, warmer, 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 hot, 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 that guides the person with a gradient towards the thimble, right? So this one is essentially the game of hunting the thimble. Bob knows where the thimble is. It's not telling Alice, but he's giving her a gradient to follow to go there. So this is essentially corresponds to a developer implementing this complicated cost function to provide a gradient to the robot or agent. What you see here below is passing the thimble. That means that Bob tells directly Alice in the beginning, here's the thimble. The thimble is actually right there. I'm not providing you a gradient to go there. I'm giving you this constraint from the beginning. Don't spill water, so don't tilt the bottle in the beginning, right? Or do not collide with the environment. You're not requesting someone to learn that. You're just saying it's like that. There's no need to learn it. I hope the distinction is clear now. Thank you for commenting on that. So here we have in the sparse reward, it's 1,000 euros or nothing. You have no gradient, so learning is a bit slow. Okay, that's always the case if there's no clear gradient to follow, but at least the constraints are respected, right? So here, the SCT is enforcing that you cannot spill the ping pong balls, let's say simulated fluid, and it's also enforcing that you cannot collide with the environment. So this red curve essentially means the robot is doing safe exploration, and the blue curve means it's not learning very fast, but that's because there's not very informative reward function. And here, the orange and red means it's doing things, it's exploring, and it's doing things you don't want it to do, the robot bumping into the environment, spilling the ping pong balls, etc. But still, it's learning fast because it has this nice gradient that you provide. Now, if we do RLSCT shaped, so we provide a shaped reward function, and the SCT constraints, you see hardly any constraints being violated, and you also have super fast learning because of this gradient. And so that's basically the story in terms of the Thimble. I'll skip over that. So some results and observations. Actually, I'll skip over that right now. It's interesting, and the take-home messages will come later, and otherwise there's no time for questions. So we did this on the real robot also. As I said, not with water, everything becomes a mess. We had 2 ping pong balls in one cup, and the robot was supposed to pour it in the other cup, and here you see some snapshots from that. So previous results, a lot of experiments were done in simulation to get the statistics and see if we can reproduce the results. We also did 5 learning sessions on the robot, and here you can see that essentially it works. It's not spilling. The success rate goes up at some point quite quickly, and this is 80 episodes. So that's something that you can do on a real robot. You need some patience, but it will work, and it really becomes interesting for industry, for instance, to be able to become efficient at a task so quickly. Current work in progress now. So as I mentioned, the pouring in the context of industrial tasks is a bit a toy task. What we are doing now is implementing this for the grasping of these clamps that you see here. So what you see on the left is Sarah in its environment, and the robot has a bunch of different grippers that it can exchange itself. And the idea here is that you have a workstation for the robot that it reconfigures itself. So basically, it has these clamps. It can put them where it wants. These clamps can then be used to fix boxes or containing parts, or it can be used to clamp subparts during an assembly. So this robot basically says, I need to assemble this product, for instance, a chainsaw. That's one use case we're looking at. How do I make my environment such that I can very efficiently make this assembly? Right, and it's important that it's able to do this reconfiguration quite quickly, and therefore, for that reason, we want to apply reinforcement learning to the placement of these clamps. It requires quite some force to grasp them, and also the insertion is rather tricky. So this is typically something where we think reinforcement learning would help. But our industrial partners would not have the patience that the robot is exploring from millions of rollouts, trying to put the clamp somewhere in the air. So we're going to use these constraints to help the robot basically guide it towards doing the task, doing the task, and then becoming much more efficient at it with reinforcement learning. A bit of a commercial for Stable Baselines 3. This is what was used in all these experiments before. This is an open source software, which is hosted here at the link. If you look for Stable Baselines 3, you will find it. It's by now become, let's say, the de facto standard implementation for reinforcement learning implementations. So you can find implementations of many reinforcement learning algorithms, and they're stable and they are documented. And we've had about 2 million downloads so far, so it's being used a lot in the community. And the main developer here is Antonin Raffin, who's also doing a PhD in my department. Okay, the take-home messages, where we're coming to the end now, are, first of all, that the requirements for reinforcement learning and simulation, of what I see a lot, is very different from robotic reinforcement learning. Like bumping into objects or spilling stuff, that's no problem in simulation. I mean, no human ever got hurt, in Isaac Gym. In real robots, these things really matter. You don't want collisions. You don't want too many rollouts. You don't have the patience to wait hundreds of thousands or millions of rollouts. So I think the requirements are quite different. And when I speak about reinforcement learning, I usually think about robotic reinforcement learning, that it has to do something on a real robot later on. And in this talk, I've explained one method this applying SCTs to reinforcement learning to make it more compatible with the requirements of robotics. So hunting the thimble, it means that you express a constraint violation as an implicit cost, right? And that means that, per definition, these constraints must be violated in order to learn them. So I must explore and figure out that I'm not supposed to spill water, that I'm not supposed to bump into objects. And yeah, that seems rather annoying that you have to learn something that is already known. So therefore, I've proposed today passing the thimble. That means that you express constraints explicitly, that you apply them during learning, and that this leads to much faster learning and hardly any constraint violations. If you want to read more about this, this is Abhishek's PhD topic, and he has some papers on that where you can learn more about this. I do need to spend 2 or 3 minutes on saying that this is not the whole story. This SCTs apply to RL. It's not the holy grail that solves everything. There are specific cases where this is useful. And that is when you have environments that have objects that are designed with a specific purpose, right? Consider a bottle. A bottle is made for having fluids inside. So you have to be careful not to spill fluids from it. A drill, for instance, it's designed with a purpose. It's designed for drilling. And there's essentially only one way to drill correctly. Yeah, you grasp the drill, and then there's a trigger here, and then you place it against the wall. You pull the trigger, and the thing starts drilling. There's no need to learn these things. Humans have made them with a purpose. Robots do not need to rediscover this. Then another aspect is if it's safety critical, if the robot is learning on the job during its operation, it should be safe. And then it's better to pass the thimble than to hunt it. I'll skip over the rest to have some time for questions. Here you see some examples from our institute, what we're working on and where we essentially pass the thimble. Yeah, that's my mantra. What is known need not be learned. Now, there are many domains where there are no such explicit constraints. There are no purposeful objects, right? Or there are so many constraints that you don't want to specify them all as a human. So one example is the game of Go. These stones in Go, as they're called, they do not have an inherent purpose. They're essentially bits of information on a board. Yeah? And they are not shaped in a certain way. Well, they need to have certain size, etc. But they themselves are not purposeful. So I wouldn't know how to develop an SCT, the shared control template, for the game of Go. The whole idea is that you want the algorithm AlphaZero to learn this game by itself so that it discovers entirely new creative solutions. And that's exactly what happens. So do not enforce constraints. They will only hurt you and not help you. Another example is locomotion in unstructured environments. So here, there are constraints, like with staircases, you should move your leg up rather than forward. But there are so many of them, and they depend on the variations of the terrain, that you don't want to specify them as a human. You'd rather have a reinforcement learning algorithm learn them directly. So I think locomotion is one of the best examples of where you can deploy reinforcement learning algorithms on real robots without any talk about thimbles. This is where the reinforcement learning really works really well. And it's the perfect, I wouldn't do it in any other way. Conclusion. So reinforcement learning, like for instance, in the game of AlphaGo, has shown us solutions that are like very creative and that no human had ever thought of. We've really learned from reinforcement learning a different way of playing Go. And that's very exciting. This is really an awesome time to be in reinforcement learning. But a question that I ask myself as a roboticist, looking also at robotic applications and less at AI research per se, is, do these real-life robotic tasks, do they require creative solutions, right? I mean, do I want a robot that drills creatively? I wouldn't want one in my home. I want a robot that drills in the way that you're supposed to use a drill, right? So it's a bit of a different story depending on the application that you're looking at. And in many applications, we've found that if you can ensure that the exploration is safe And on the job, you can increase the performance that the robot learns to do it quicker and quicker over time. That already has a very big impact, even if it's not finding these awesome creative solutions to the task. And for that reason, we focus on developing reinforcement learning algorithms that work directly on real robots, that ensure safe exploration for the environment, for robots, for humans. And we work also a lot on providing intuitive tools for specifying goals and constraints, which I've not explained much today. So thank you very much for your attention.